It's my great pleasure to introduce Peter as the next speaker in the workshop. Peter is currently a senior staff research scientist at DeepMind, but before his forays into computation, Peter was actually a psychology student. That's what he got his PhD in, and then moved to MIT to work with Josh Tenenbaum's group. And over the years, he has done a lot of amazing work in graph-based reasoning, unsupervised 3D inference, combining symbolic methods with deep learning, and I think more generally, just trying to tie in together our understanding of cognition with sort of more modern deep learning. And I've personally drawn a lot of inspiration from his many amazing papers over the years, and so I'm really looking forward to hearing what he has to say in the talk. And Peter, we might interrupt you 5 minutes before time just to give you a warning of, to wrap things up. But yeah, okay. The floor is yours, and thank you for joining us.
So thanks a lot. So actually, I was really interested to hear the last talk, and I had sort of taken some of the content out of this talk that maybe would have had some motivation based on similar ideas as Kevin was talking about. But I'll just give my sort of 10-second view of things that might help also motivate what I'm about to talk about. So yeah, and generally I'm in broad agreement with what Kevin's saying. The one point I would sort of suggest is that I'm not sure that we don't have metric knowledge. I think that we still can often have very precise quantitative knowledge, but it's still inferred, right? So we can often know exactly where something is in order to pick it up and things like this. But we absolutely build an understanding of our environment based on the evidence we receive. In some cases, we only need approximate understanding. In some cases, we need much more high resolution, accurate understanding. So I think that a really interesting question is how the data that's available informs these questions of how our mental representations work, as well as what we need to do with our mental representations, sort of puts constraints or incentivizes different strategies for understanding in the world. So anyway, so what I'm going to talk about today is some work we've been doing on the machine learning side, which I sort of put broadly under the umbrella of structured understanding and interaction with the world. The work, so in general, I'm very interested. I've been interested in a while for a while in how sort of people and agents should perceive complex scenes, understand how they work in terms of causality, physics, etc., and interact with them. And this is a snapshot from a paper we did 7 years ago, where we proposed that in order to understand everyday physical scenes, you have some kind of physics engine in your head that operates on a mental model of the contents of the scene. And the way it works is you go from the input data, the images, for instance, into some structured understanding that you can reason about in terms of the causal structure, the causal dynamics. And then you can answer questions or interact with the world by trying things out in your mental model and making inferences. So today what I'm going to describe is how on the machine learning AI side, we've been trying to attack different components of this problem, these 3 different components I'm laying out to try to improve AI's capacity for performing these types of abilities. Okay, so the first part of the talk, I'm going to talk about how the project on perceiving complex scenes or really complex objects. So this is work, it was just actually presented at ICML. It was led by Charlie Nash. It's called PolyGen. So it's an autoregressive generative model of 3D meshes. And this image shows a whole bunch of mesh objects that we've rendered. And each of the objects was actually generated by this model that we built. So these are not these are not meshes that were designed by somebody by hand, but actually produced by a trained neural network. The arrangement of the objects was done by Charlie, but hopefully in the future we can actually also capture where the objects are arranged with respect to one another. But this is to show that you sort of can create a realistic scene out of meshes that are generated from a learned model. Okay, so to start off, so what's a mesh? A mesh is a geometric representation, and you can think about it as a graph. So M over here is the mesh graph, and it's comprised of vertices or points in space, and faces, which indicate which points in space can be connected up to form a surface. On the right, you've got an OBJ file of this cube. So you see the cube has 8 corners, so there's 8 V vertices, and there's 6 faces, and so the vertices are X, Y, Z coordinates of the corners, and the f, the face, these integers are the indices of the vertices that comprise the different faces. And this is an actual OBJ file. So this is exactly how many meshes, is a very popular format, many meshes that you see rendered in computers, this is how they're represented. And you can represent meshes in different ways. So a triangle mesh is a very standard format, and every face has exactly 3 corners. It's a triangle. We actually found in the work I'll show that n-gon meshes, meshes that have variable numbers, whose faces have variable numbers of sort of corners, work better for the model, but you can represent meshes in different ways. So I described, so again, polygons can be an autoregressive generative model of meshes. So I described what a mesh is. So what's an autoregressive generative model? So if you want to generate this sort of wiggly signal here, an autoregressive model would generate it in the following process. It generates it sort of element by element, piece by piece, in a sort of sequence, typically, by considering the things that have already been generated. So here it's sort of looking at this black context that it already generated and then generating the next point in this kind of sequence of line segments. And it just sort of continues this process. So this is an autoregressive sort of generation process I'm depicting of this funny kind of signal sequence. And what we're going to do is we're going to train our autoregressive generative model to capture the probability distribution over meshes in this ShapeNet core dataset, which is 55,000 meshes. Okay, so how do we model the probability of a mesh? So the joint probability of the vertices and faces, we factor into 2 terms: the vertex model, which is the probability of just the vertices, and then the probability of the faces conditioned on the vertices. And this is, and then I'm going to now describe sort of how we learn each of these components. So we have an autoregressive model of the vertices themselves. So what we're going to try to do is have our model output a predicted distribution for the sequence of vertex coordinates. So if you take the vertices and just sort of line them up in a row, in fact, not even just the vertex by vertex, but like the z, y, x of the first vertex, z, y, x of the second vertex, etc. We model that as a probability of each vertex given the previous ones before it. And this is the autoregressive nature of the model. And the training is going to try to maximize this probability. So we're going to optimize the theta parameters in order to maximize the probability of the data set under our model. So we're going to say, here's our model. If you evaluate it on the data set, let's make sure the model gives the data very high probability. A very typical approach in sort of generative modeling. The structure of our model is going to be based on a transformer that takes the set of previously generated vertices, and what it does is computes does multiple rounds of sort of soft message passing in order to then predict what the next vertex in the sequence will be. And this is you can just think about this almost identically to how people use transformer-based models for language modeling, such as like sort of GPT-3 and those things. And so each sort of z, y, x in the list of vertices will be generated by conditioning on the previously generated ones. We also have an autoregressive generative model, autoregressive model of the faces given the vertices. It works basically the same way. So the face indices of which vertices will come next in the OBJ file are given by this factorization of the probability of the faces given the vertices. And again, we're going to maximize the log probability of this term in order to train it. I should say also the vertex and face models are trained jointly. And the way we implement this model is with another transformer that takes the generated vertices as well as the indices of the previously generated faces, and then uses them to predict. Well, it's going to actually pass it to a sort of pointer network style mechanism to basically, so it produces a sort of key that's going to be used to look up which vertex should be connected to the face next. So here it like points to this vertex, and then it points to this other vertex, and then this third vertex, and this fourth vertex, and then it emits a stop signal, says I'm done with this face, and then that closes it and makes it a single shape. I should also point out that the actual form of the probability distribution is a softmax over. We sort of discretize all this stuff, and we have a softmax over this discrete set of vertex coordinates. Okay, so here's some results from training this model. So what I'm showing here is basically I'm sequentially sort of generating the mesh vertex by vertex and then face by face in the same order the model does. And you also notice it always goes from the ground up. We always sort our vertices from bottom to top to just impose some sort of regular sequentiality to the mesh. And you can see it's generating some pretty realistic meshes. So these are meshes that are generated conditioned on an object category. So I didn't write this in the last few slides, but you can also condition not just on the vertices that have already been generated, but also on any other arbitrary vector you want. And that can be like an embedding of the object categories. So this is like lamps, and this is TVs, this is sofas. And so here's some more examples of this, conditioning on jar and bench and monitor, sofa, clock, etc. Some of them aren't really that great. Like this lamp doesn't really connect to the top part exactly, and this doesn't seem to have filled in the faces of this clock or whatever it's trying to read, this double clock thing, but in general, they're pretty good. We can also condition not on a category label, but on voxels. We can embed a three-dimensional sort of volumetric representation of what kind of shape we're interested in generating, and then create a mesh that's consistent with it. So here, the way we did this is we took some meshes, we voxelized them, and then we conditioned on the voxels, and then generated samples of the object that would sort of correspond to these voxels. Again, you can see sometimes it makes some errors, but in general, it's quite good. Here's some more examples. And we can also play the same game with images. So instead of conditioning on a sort of three-dimensional volumetric representation, we can have a two-dimensional like RGB representation, embed it with a convnet, and then use that as a conditioning term. So here's a true mesh on the right, and here's an image that was rendered from it, and then we condition the model on the image, and then let it sample out these meshes that would be consistent. So this is, I guess Charlie sort of is maybe sort of humble. He'll say like, this is like, autoregressive generative model conditioned on images. I'm like, this is a vision system. But basically that's what it is, right? It's taking an image, it's creating a three-dimensional object that's consistent with that image. Here's some more examples of that. It can also do unconditional samples. Like it can sample objects from a prior, but these are sort of like posterior samples. Okay, so just to conclude this little section, so polygen. So the idea is that we're modeling in the prior posterior object geometry given object categories, voxels, or images. And in particular, it can sort of perceive or see structure state representation from raw image data or other types of data. This transformer-based vertex and face model, transformer-based vertex and face models are being used to generate these mesh graphs. So you can also kind of view this as like a particular type of graph generative model for a subset of all graphs, the mesh graphs. Transformers operate on sets and compute sort of soft interactions among elements and do this sort of, message passing like operation inside. And so I think this sort of set-based, graph-based internal representation is very important for being able to capture these kinds of more complex objects. And we're kind of very interested in next applying this to the actual contents, like the multiple objects in a scene, more complex arrangements of objects like I showed in the first slide. And if you want to play around with this code, you can get it on our GitHub repo. Okay, cool. So that's just like one recent project on trying to understand complex scenes and trying to see where we're kind of going with this. We've also been doing a lot of work on understanding how complex scenes work. And what I mean by that is how the physical dynamics or the causal dynamics work in these in complex scenarios. So for a while, for several years, we've been writing papers on increasingly complex learned simulators. So I'll give you some quick background on this. So if we want to model this physical system, an n-body system, so imagine this is like a planet, the purple thing's a planet, the yellow thing's not a planet, it's maybe circling some kind of larger star. We represent the planets and stars as nodes in a graph, and their states are represented by the vertex attribute V. And interactions or relations among them, like the possibility that they could impart gravitational forces on one another, is expressed with edges in the graph. So here you sort of connect everything up because gravity applies across all bodies in the system. In order to predict what's going to happen in the system, we train models where the idea is we take the graph representation and we have one neural network that applies to each edge. It's sort of convolutional over the edge structure. So we say this phi-e function is applied to every edge. So an edge is like the edge attribute and the pair of nodes connected by it, their states. And we compute a message or updated E prime value, some latent property of the interaction among these things. And you can kind of think about this as like a force. We sweep this phi E over the graph. So you can kind of see me sweeping this function over the graph. And then we aggregate up for each node all the messages it receives. We aggregate those up using usually like a summation or something. And we pass them to a second neural network, this phi V, which is a node update function. So this is, you can kind of think about this as like an integrator. It's taking all the forces and the current state of the object and then predicting like a new updated state of that body. And we can again sort of convolve this function over the graph, like over each of the nodes in the graph, update each of them, and then we can use supervised training to optimize the parameters of the neural network so that they will predict the next sort of the state of the system, of the body's positions they're at, where they are in space in the next time step. So yeah, so that's basically the scheme. In the next like 5 minutes, I'll just basically be kind of repeating that over and over. So if you want to model an n-body system or bouncing balls in a box or strings, mass spring system interacting with some rigid thing, you just make a graph that corresponds to this, and that's what each of these show. And then the top row is the ground truth simulation. So we only train on one-step prediction, but then we roll it out for like 1,000 steps. It makes a prediction, we feed that back into itself, and we just do that over and over to generate a sort of physical trajectory. And the bottom is the model's predicted rollout from the same initial conditions as the true simulator on the top was run through. You can see it's pretty accurate, especially in an n-body and string case. In the bouncing balls, it can deviate a little bit, but like again, this is a sort of highly nonlinear dynamical system. The key thing is that it's very plausible. It looks right. So these are sort of small errors that are probably just compounding. What's more interesting is that this model, because it's sort of the locus of learning is at the edges and nodes, we can once trained, we can input a larger system than it was ever trained on, and it can still make good predictions because for the sort of same reason that physics engines work on different scenes with different structure, the reason that physics works on scenes with different structure. It's because the local rules are what determine the complex dynamics. And we capture the local rules, and then we can sort of zero-shot generalize to larger systems than we were trained on. So these are the bottoms model rollouts from the system I showed in the previous slide. We can play the same game, not with these little toy systems that we created, but with like Mujoko control suite systems, so actuated control systems. This is how we represent one of these things as a graph. And this is an example of, on the left, the ground truth rollout of a swimmer under random control inputs, and on the right, we have our model's prediction of the rollouts. We can also do this with the same model we applied to multiple different physical systems, because again, it just has to know about how the interactions among the elements work. So this is at the top row is a single model predicting lots of, like, I think there's 5 or 6 different systems, 5 different systems. And again, we can also generalize in the bottom row to swimmers of sizes that we were never trained on, because for the same reason as we could before, the little force or message functions and integrator or node update functions are sort of common across the systems of different sizes. Also, it also works on real data. So on the left is a rendering of a real JCO arm that's been it's just given random control inputs, and on the right is our model's predictions of the trajectory of the arm. So you can see it's pretty consistent with the real rollout. Okay, so that brings us to the sort of the thing I want to spend a little more time on. This is a recent paper we had at CML with Alvaro Sanchez, Johnny Godwin, Toby Pfaff, and Rex Ying as the people who led the work. And all of these videos here are actual rollouts from our model. We've sort of post hoc just like put surfaces on them and rendered them with a ray tracer, but the geometry and the dynamics are given by are predicted by the model. So I'll describe how that works. So you take a system that's represented as a set of particles. So this is like a sort of box of particles that represent a fluid. And what we want to do is roll out that fluid's trajectory in time over thousands of steps. So basically, the idea is we're going to train some simulator, and it's going to predict on each time step what happens next, and we're going to take the output, feed that back in, just as we did before. And here's how it works. So it's very similar to before. So we take the set of particles, we compute a nearest neighbor graph among the particles, and that's represented here. And that's like how we encode the graph from the set of particles. And then we run 10 unshared message passing steps with a graph neural network. It's just going to sort of compute local interactions as sort of almost like a complex diffusion process, like how far, how things impact things nearby. And we take the output of that, and then we use that to update the input state, and then we do supervised training to try to make that match the real trajectories. But again, we only do one-step prediction. We supervised train on one-step prediction, and then we roll it out for many steps. So here's some examples of what happens after training. So on the left is the ground truth. On the right is the model's rollout. Again, just we reconstructed the surfaces and ray traced it, but I'll show here. Here's like the particle representation of the fluid. Actually, here if I go like this, I don't know if you can see this, but the fluid is kind of turning into from surfaces into like the actual particles. So the particles on the right are exactly what the model's operating on. So that's our water, 14,000 particles. Here's our sand simulation. This is a different simulator, actually. Our model was sort of robust across several different simulators we tried as well. This is sort of sand material. Here's the particle representation. And here's our goop material, which is sort of a gelatinous, I don't know, it's goop. And here's the particles. So what's cool is that we can also, again, we see really sort of dramatic generalization. So I don't think I wrote the exact numbers on here, but we can generalize to systems that are 10 times, or sorry, about 40 times, I think, larger than we trained on, that are 10 to 40 times, like sort of, I should say, scenes that are like, 40 times larger in space, 40 times as many particles, and also many, like, orders of magnitude more time steps than we were trained on. So this is showing on the top right is the training domain. So we just trained it on little sort of small scenes with like a single ramp. Let me show that again. And then we just ran the model on much, much larger scenes like you're seeing on the top with like these inflows and things. And again, you can see on the right, our model's predictions, very sort of compelling and accurate simulations. We can also show things, multiple materials interacting with one another. This was trained on much simpler dynamics, but we can start to have like goop and sand and water all together in one big mess. This is like, my kid's dream, play with this sort of little sandbox. And we can also even have interactions with like rigid sort of objects that are represented by sets of particles that are, there's nothing sort of special here. We just basically give the particles that are rigid like a special indicator attribute on their vector representation that says these are sort of solid, and then the model learns to treat that as something where they should maintain the relative relations with each other. Okay, so the conclusion from this, so these graph neural networks can model these complex causal interactions among objects and materials that we keep finding. And you can sort of do forward simulation. We also can, I didn't show this, but we can also do sort of model predictive control under these models as well. And I think the way I look at one of the things I like the most, as I sort of made a point about, was that by learning about the entities and the interactions, you can generalize to much larger, more complex settings than those on which you were trained. If you're interested in, so we use this library, this graph neural network library released for TensorFlow called GraphNets. The link is here. I can share these slides. And for this particular paper, we're about to release the code and data sets for it too, so you can play with it. Okay, so the third part, I think I'm running a little bit short on time, but this isn't a sort of shorter part anyway. So I had, at the beginning, I had sort of pointed to this like sort of perception, input, reason about complex scenes, and then interact with complex scenes. So this is some work that we've done recently to address how to interact with complex structured scenes. So the first point I want to make is that humans are a construction species. So as children, we love playing with blocks and water and digging holes and covering things up and knocking things down and building them back up. And then when we're adults, we make these beautiful structures. This is the Big Ben in London. And throughout history, we built shelters for ourselves as a means for survival, and we're not even happy just building stuff on Earth. So we shoot rockets into space, and then we build houses up there to live in. We're a construction species. So we wanted to kind of explore these types of construction behaviors in AI. And this is a project we published at ICML last year, led by Victor Bapst and also with Jess Hamrick. And the idea is we're going to train agents to solve little physical construction problems. So the way that these tasks, this environment works, which we also just released, and I'll point to at the end, you have this floor, that's the black line. You have a bunch of blocks under the floor. This is like your sort of palette of blocks you can use, and you're going to stack them up. And these red things are obstacles, and you have to avoid touching the obstacles in general. And we have 4 different tasks, which I'll describe in a second. One other option you have, though, is you can kind of think about this like Legos. You can make the blocks sticky, so you can stick blocks to one another so they'll hold their relative position once they come into contact. So it's sort of like snapping blocks together like with Legos. Okay, so here's some of our, I'll just actually put all these up at once. So here's our environments. We have the silhouette task on the left. That's, you're given a sort of target configuration over here, and your job is to stack the blocks from the bottom in a way that will match the target configuration. So you can see it's matching the target up here. In the connecting task, we call it, you have these little blue blocks that are floating above the scene, and you have to make contact with them by stacking blocks from the floor up to the ceiling. So it's almost like you have to connect the floor to these things and avoid the obstacles. And in these 2 covering tasks, the idea is just think about these red things as something that you're trying to build a shelter over. So here, like, you don't want them to get wet, you know, in the rain. Build a little shelter over these red obstacles, but don't touch them. So it's sort of like build a shelter, but leave that space open. This regions of space have to be kept clear. This covering hard task, the difference is that in these other tasks, you have like a sort of infinite supply of blocks. In the covering hard task, we call it, you have a limited number of blocks. We have fewer obstacles because you only have a small number of blocks, and they're kind of packed more closely together, so you have to plan ahead about what you're going to do. One of the key manipulations, we're going to have 2 different types of actions. So one, you can, or two different interfaces for actions, and we're going to compare them. So one is you just sort of pick absolute positions out in space to place a block. And that's like you target this place, and then you just select, place a block there. The relative object-centric actions, you're going to choose a block in a relative position with respect to that block, and then place your block there. So it's like really more like Legos. Like attach this to this other block at some, you know, offset from it, say. The model we built is graph neural network based. So it's one of the first agents we built is a model-free RL agent that's going to be based on Q learning, like a sort of deep Q network. And the idea is that you're going to get some observation. That's what's on the left here. And say you want to stack the block D somewhere maybe on block B. Okay. And the idea is you take this, the observations. We have a whole bunch of different variants of this model. The one we explored the most, we have a symbolic sort of graph-based representation of this scene. We hand it to this agent that has a Q function that's defined over the graph. So these vectors that are along the edges of this little scene graph are meant to reflect the value of placing a block placing block D with respect to the other blocks. And the reason that it's not like if there's sort of 4 elements in the vector, that means there's 4 relative coordinates that you could place block D with respect to, say, block B. So here you see block D.
You've got about 5 minutes left.
Great. Okay, perfect, actually. So if you want to place block D on block B, and maybe like a little bit to the, say, maybe this is like slightly to the left, and that's white. White would indicate, say, like if the Q function says, if the Q function has a white value, maybe that means it's the highest expected value. So the idea is that we're going to train up a graph-based approximation to the Q function so that the agent is making relative actions by in a way by maximizing the expected value. And hopefully this makes sense. It's easier when I have feedback from a live audience and see if people are squinting, but I'm going to assume that this is okay. So here's here's this agent in action. So on the left, and I should say that I actually have to explain one more bit. So the absolute action agent doesn't make these relative judgments like this. It takes the graph and it like computes like a graph-wide embedding of the graph, and then predicts where to place the object in space by sort of pooling all the information across the graph, whereas the relative agent makes edge-based sort of actions, if that makes sense. Okay, so here's the 2 agents in action. So in general, you're going to see the agent, making these object-centric relative actions tends to make the agents a lot better. And you can see on the right, the agent is solving this silhouette task much more accurately. The more interesting tasks, like connecting blocks from the floor to the ceiling, you can see again, the agent that has the object-centric actions is just solving the problem. It's connecting up those blue blocks to the floor much better. And so here's this covering task, this build a shelter over the red things, tasks. You often see in the absolute agent, we don't really know why, but there's this like sort of pathological behavior it tends to fall into, where it just tries to build these sort of igloos over everything and just kind of cover it with a big dome. The relative object-centric agent uses more sort of sophisticated like structures. It kind of like weaves blocks around each other. And, you can see again, you got this dome being constructed over here, and this one's sort of building these little like, I don't know, T things or something. And then this is the covering hard agent. In general, actually, this agent is these agents, the model-free case, there's actually not that much difference in their performance, although the types of structures they build are kind of different, but I'll address that in a second. So the main result we see, though, is that using sort of relative object-centric actions and really exploiting the sort of graph structure, Q function, or policy leads to higher reward on the y-axis. So the top row is the average reward across all the different levels. We have a curriculum, and so if we also just peel off and just analyze only the hardest levels, you see also that the relative object-centric agent does better, except in this covering hard task. In general, it's not getting as much reward as it is really not doing that well, and any of the model-free agents didn't do that well. So to address that, again, we had sort of built this covering hard task with these like finite supply of blocks in order to get it to try to think ahead and plan its use of resources. We built a model-based agent. So here it's going to use MCTS to actually search over a model of the environment that's graph structured. So it's basically just like running simulations of how it could connect things up in this Lego style through an MCTS loop to estimate the Q function. And when we do that, the purple, I'm not going to explain this, but the purple, the dark purple is basically the agent with planning, model-free model-based planning, and the light purple is the model-free agent. You can see it's building sort of better structures here. Okay, so that's basically it for that section. The talk's almost done now. So the conclusions we draw from this is that having structured models are valuable for interacting with these complex physical systems like construction tasks. We use these graph-based scene representations and these relative object-centric actions. And you can also view these construction agents as graph building agents, sort of in some sense analogous to this polygen at the beginning. So it's like they're basically adding nodes and edges to a graph in order to solve some downstream, achieve some downstream task reward. And we've got ways of now having model-free and model-based sort of graph construction agents. And if you're interested in playing with this environment, you can check it out on our GitHub repo. But unfortunately, we don't have the agents on there. They're sort of very complicated RL setups. We have a paper you can check out from ICML last year. Okay, so yeah, the last conclusion I'll wrap up with. So overall, representing the world with richly structured models of objects and their relations, I think allows for sophisticated generalizable patterns of perception, understanding, and interaction with the world. And I think what we're kind of showing is that we're sort of starting to realize some of the components of this pipeline that we've been kind of interested in for a while. They're like perception, structured reasoning, and structured interaction. But now I think the question is, can we build a single system that puts them all together? So perceive the raw inputs of structured representations, use them to reason about this causal nature of the environment, and then plan creative constructive actions, interaction with the world across a wide range of contexts. And so if you have any ideas about how this should work, I would invite you to please reach out and let's talk. So thank you very much.
Thank you, Peter, for the enlightening talk. I'll maybe ask one quick question to connect it to the previous talk. So you showed here some extremely precise prediction models for 3D shape and for fluid dynamics in the first and second parts. And this seems in contrast to Kevin's argument that we should be representing things in our latent space in a more approximate way. So I'm wondering if you think that there's a way to bridge that gap.
So I think it was basically the thing I was trying to say at the beginning. I don't think, my sense wasn't that Kevin was saying we should represent it in a more approximate way. I thought it was more that we do often have approximate representations, or it's not like we're literally representing pixel this, pixel 1, 2, 3 and pixel 4, 7, 3 or whatever. And I'm guessing Kevin will probably agree that like the reason that evolution has brought us to this point is there's probably some optimization problem, some benefit to not having these like pixel, as Kevin was saying, we don't need to like store the world. We can just look at the world and like sample it again if we need the like texture details and things like this. And this is like, all the demonstrations he's showing, again, like the texture of a carpet is a very complex thing. There's no reason that you would need to store that in your brain. So I think the important question, which I think we can start to get at, is why do we have, like from the cognitive science side, why do we have the representations that we have? So what are they optimizing for? So there's probably some downstream tasks that they're good for, or lots of a wide spectrum of downstream tasks that they're good for, but also computational costs and learning costs. They're probably, the way we think about the world is probably something that is efficient to learn and efficient to update, and also something that's efficient to compute with. And people have talked about this forever, right? Bounded rationality and optimal like resource rational thing. Like if you're interested, like Tom Griffiths, Falk Leader, has some interesting recent papers you can read on this. I think what we're doing right now is mostly still geared toward the task reward thing, but I think a very important question is, how can we in AI account for the costs of inference and learning? Maybe we don't always have billions of parameters and zillions of TPUs that we can train and an infinite supply of data. Maybe we have very much more kind of expensive data and compute situations, and maybe those are the incentives that are being optimized by these structured, approximate, kind of more abstract models that we have in the world.
Great. Next, we have a question from Chris Atkinson in the audience.
So you presented three, I'll call them problems. And with the first problem, you essentially described the object, but with the second two problems, you described how to actually construct or control or somehow have some process that unfolds over stages or time. And it seems to me that those two things seem very different. You could have described shapes of objects by describing how you would have made them. Generalized cylinders, for example, is sort of an extrusion process. And now that we have 3D printing, we're all familiar with additive and subtractive processes starting from some primitive shape. And the flip side, especially with the last task of constructing things, you could have had something that reasoned by saying, I want to build a house to cover something without thinking about how to actually construct a house. I just visualize the house. And in optimization problems, that's fantastically useful, even if you, in the end, generate an infeasible solution. Something that gives you a goal or some sort of heuristic, as in A star, is very useful to figuring out these processes.
Right.
So it seems to me you're sort of schizophrenic.
Okay. Well, actually, so I actually think that, so let me say two things. I think sorry, are you finished? I didn't want to like cut you off. Can I go ahead?
I'm good.
Okay,
Full speed ahead.
Okay, so actually, if you look at Polygen, you look at this slide that is put back up, they're quite similar in a way. They're like, this is effectively an autoregressive generative model of graphs as well. So I think the Polygen, vertex by vertex, then face by face, it actually does the vertices first, and then it does the connections between them. But again, this is just a matter of like, we talked about, we're thinking about ways of like sort of interleaving the face and vertices. There's no real barrier to this, we don't think. So I think that there's still, in the first thing, there still was a sequential process. It just wasn't that interesting. We just kind of sorted the OBJ files, and then just that was the sequentiality to it. But also remember, like there, when you're conditioning on the voxels or the image or the class category, that you could almost look at that as like an overarching goal, right? So it's like my goal is to generate something chair-like, and I want that to influence all the different decisions I make in this like iterative process to generate the mesh. Okay, and here I agree. We don't actually well, there's an overarching kind of goal of like cover this thing up, but you could imagine doing things like saying, like maybe in the silhouette task, for instance, if instead of instead of saying like block by block what we want, you could just kind of have like a region of space that you want to cover. So I want a shape that kind of looks like this, and then see if we can get the model to condition its full sequence of actions to achieve that single ultimate goal. But I think that like there's a sort of a broader point here, which is that I don't think you. I think that don't read too much into the sequentiality of any of the things that I'm talking about. Maybe in the physics case, but especially in the mesh generation and the construction, we could order these things differently. And I absolutely think that having more abstract representations that then are maybe used in a hierarchical fashion to kind of like condition regions or subgroups of blocks or vertices is a really good idea. In some sense, I think that what we're showing is that you actually don't need that to do well in the tasks that we've laid out, but I also would expect that in more complicated or more like modular factorable problems, like cooking a dinner might really can be broken up into multiple components. So maybe you do want some kind of hierarchy, like I need my vegetables and I need my starch or whatever. So I think in general, I'm kind of in agreement that hierarchy and these kinds of things are important, but I also think that you should be able to start twerking the things we've been doing into that, to satisfy or to achieve that.
But the OBJ file format seems very artifactual. For example, vertices are not something you make, and edges aren't something you make. You can cut faces, and I could have had an OBJ file where I repeated the vertices and got rid of the vertex list and essentially listed all these triangles as isolated surfaces. And, it's the same object, but sort of seemingly a different representation.
Yeah, do you think?
Similarly, I could have represented the thing by basically constraint planes, which would have generated all the faces. And edges and vertices sort of come out of that, but aren't represented directly.
Do you think that so I don't see any reason why what we're doing can't be applied to a different set of choices about what the representation is. So we could certainly try, it would probably take a little bit of adjustment, but we could certainly try doing like faces or even geons or a sculpting thing that started with just a mass and then kind of cut it away. Do you think that what I'm showing wouldn't work there? Like I know that I'm confident that it can be applied. I don't know if it would work. It's something we want to test, but do you think that it wouldn't work?
Well, it's a little hard to understand what the underlying method is. Graphs could be used to represent constraints, which is essentially what all of your things are doing. And, are you asking if graphs could be used to represent constraints? The answer is yes. I think the real question is, what's the task? What's the similarity metric you're trying to compute? And does the representation naturally support that similarity metric?
Yeah, right. I think that's one of the most important questions. I think that's sort of like, I guess, that's kind of what I'm trying to get at with this point at the end about the, like, how do we glue these things together? So I shouldn't say that it's not just like a matter of saying, oh, let's, like, now that we have our polygen and our simulator and our construction agent, just connect them up. There's certainly, like, they don't connect up right now, right? I think that there's really important, interesting work at the interface. I think what you're mostly talking about is, like, if you have some real data or some real goal, how do you learn to represent it in a way that is going to be able to be sort of reasoned about and planned with very effectively? I think that's an important question. So one small thing I'll say, I'm probably out of time, but I'll just say, like, if you look in graphics, a big aspect of what was a big important sort of subfield of graphics is we're also, like, engineering structural mechanics is representing complex systems, like discretizing, representing as a mesh or a grid, often like allocating your resources, your computational resources dynamically to the high, pretty high resolution on things where there's a lot going on, and leaving coarse resolution representations for the things that there's not much going on. So these sort of, I guess, like economical representations using structured meshes and things like that are very kind of very profitable but difficult. So I think that we can start to think about those directions as well, like how to represent more general problems as structured things that we have models that can deal with. I don't have answers for you, but I think it's an important question that we're definitely excited to work on, or sort of working on in some cases.
So I think we're about out of time. Thanks again, Peter, for the great talk and for the very detailed answers to our questions.
Thanks.